And my slope tells me that if I were to move 1 unit to the right, I could go down 5 units, right? But that's kind of a pain, especially, I mean, halves aren't too bad, but what if it was like thirds or sevenths? Like, it's pretty hard to to measure fractions on a graph, right? But remember that the slope is just the change in my y value divided by the change in my x value. And so equivalently, I could instead go down 5 units and to the right 2 units, right? So I can decrease my y value by 5 and increase my x value by 2. One thing to keep in mind, I always go to the right. So it's true that you could go left and up, or there's always 2 directions you could go, but I think it's easier to remember 2 directions than 4. So if it's negative, you go right and down. If it's positive, you go right and up. And then you don't have to figure out if left and down is negative or positive and all that stuff, right? If you're always moving to the right, then it's just either up or down as far as positive or negative goes. So we're going to go down 5 units, and then we're going to go right 2 units. So 1, 2, 1, 2, 3, 4, 5 gets me here. Any questions? I'm never quite sure how familiar everybody is with this, so I don't want to do overkill, but does anybody want me to talk about it anymore than we already have? You feel good? Okay. So next we want to talk about intercepts. So the intercepts of a graph, with a line there's usually 2 of them, not always, but the x-intercept of any graph is just where it crosses the x-axis, and then the y-intercept of any graph is just where it crosses the y-axis, right? So what can you tell me about every single point on the y-axis? They all have one thing in common. What is it? If you're a point on the y-axis.
So it's going to be 0,
yeah, the x value has to be 0, right? So you haven't moved left or right from the origin if you're on the y-axis. And so every single point on the y-axis has an x value of 0. Which is handy because that helps us find the y-intercept, right? If we plug in an x value of 0, our output will always be the y-coordinate of the y-intercept. And the same is true on the x-intercept. What can you tell me about every point on the x-axis? It has a y value of 0, right? Which is nice because it tells us how to find our x-intercepts by just putting 0 in for y. So our x-intercept is where y is equal to 0. And this is true of all functions. So it has nothing to do with the fact that it's a linear function. When we start talking about nonlinear functions, our process for finding the x and y intercepts is going to be exactly the same. Because regardless of what type of function it is, the x-intercept is always on the x-axis, so y is 0. And the y-intercept is always on the y-axis, so x is 0. So those properties have nothing to do with the fact that this is a straight line. It's going to be true of every function we work with. So algebraically, to find the intercepts of the graph of f, and again, this is true of all functions, but we'll use it now for lines. To find the x-intercept, we know that that corresponds to a y value of 0, and so that's where the output of our function is 0. And so we're going to solve the equation f of x equals 0. Right? So remember, f of x represents the output of the function, so we're making the output 0. So all we're doing is translating from the graph itself into function notation, so that if we're given a function in function notation, we can find the intercepts even without actually graphing the function. So then to find the y-intercept, well, again, the y-intercept exists where the x value is 0, and so I'm going to evaluate the function for an input of 0. So to find my x-intercepts, I'm making my output 0 and solving for my input. To find my y-intercept, I'm making my input 0 and solving for my output. So let's do an example. Find the intercepts. So we'll start with our x-intercept. That's where my output is 0, so I'm solving the equation f of x equals 0. We saw something like this, I think on like our jar problem, right? They gave you like c of x equals 141. Remember that f of x, the entire thing, f of x, that represents my output. So when I look at my equation, I'm replacing this entire left side with 0. That's different than saying that x is 0, right? If they told us what x was, we would have a number right here. Because we have an x right there, we do not know what x is. We know what f of x is, so we know what our output is. And so we're going to take the entire left side of our equation and just replace it with 0. Is everybody seeing the difference between like that and replacing x with 0? It's easy to get those mixed up. One quick way to tell is just looking in those parentheses. If there's not a number in the parentheses, then you don't know what x is, no matter what. Like every time we give you an x value, it'll be in those parentheses. So let's solve this. We got negative 5 equals 3x, and then x equals negative 5/3. So my x-intercept is going to be negative 5/3. That's my x value, and then 0, because that's always the case with x-intercepts. And then to find my y-intercept, well, this is a linear function, and so you can just grab it from the equation if you want to, but I'm going to show it to you algebraically just so you can see it. Like I said, we'll do it for other functions. So if I wanted to do this algebraically, or if I forgot that like b is the y-coordinate of my y-intercept, you can always fall back on the fact that x is 0 at your y-intercept. So when all else fails, just plug 0 in for x to find your y-intercept. So we evaluate f of 0. So f of 0 equals 3 times 0 plus 5. And one cool thing to notice, like when we relate it to like plugging 0 in, is that the fact that that constant term, so the term that doesn't have a variable in it, what we call b, is the y-coordinate of our y-intercept, is actually not limited to linear functions. It's true of all polynomial functions, because when you plug 0 in for x, every single term that has a variable in it is going to become 0, and you're only going to be left with the number that doesn't have a variable. So like if you had a function like 10x to the 5th minus 9x squared plus 3x plus 6, that 6 is the y-coordinate of your y-intercept. So just like with linear functions, that constant term gives you your y-intercept. It's true of all polynomial functions, because everything with an x in it just becomes 0 when we plug 0 in for x. And so we can kind of extend that idea of like the b to all polynomial functions, which makes it a little bit less work to find those y-intercepts. We'll do more of that later. So equals 5. And so my y-intercept is 0, 5. And again, if you just want to grab that from the equation, that's totally fine with me. If you didn't show any calculations there, like I'm happy with knowing that you understand where to find it in the equation too. Any questions on just finding those? Good stuff? Okay, and then I want to talk just a little bit about the relationship between slope and average rate of change, because it's easy to feel like there's a lot of things going on when really it's all like the same thing. So remember we said yesterday that any function can have an average rate of, or has an average rate of change between any 2 points, but only linear functions have slopes, right? So the slope of a linear function is the average rate of change, which happens to be the same everywhere on the graph. So regardless of which 2 points you choose, whereas the average rate of change of a nonlinear function depends entirely on which points you're using to calculate it. So we've seen a couple different notations, right? We used that first one is the same as what I gave you yesterday for average rate of change. I just, instead of using A and B, I used X1 and X2 to represent my two different X values. So these two things are essentially the same. One is like written algebraically, one is thought of graphically, where we have X values and Y values. So I just wanted to show them to you so you can see like that we just have a lot of different ways of kind of saying the same thing. And it's easy to get like mixed up and be like, but which one am I doing? And it's like, well, you're really doing all of them. Like whenever we ask you for an average rate of change, you're essentially finding a slope. Whenever we ask you for a slope, you're essentially finding an average rate of change. So just so that when you see one of the terms, is that the word I want to use? So if I ask you for slope, you can think, oh, that's the same as average rate of change. If I ask you for average rate of change, you can think, oh, I'm just finding slope, right? So this might be the way you've seen it before, right? Like when you learned how to find slope at some point in your life, if you ever did. Average rate of change formula is exactly the same. I've just written it in function notation instead of with y's, right? And we talked last week about how f of x2 is the y value of the function evaluated for whatever x value you're given. And so these two things are exactly the same, depending on how we're writing it. Does that make sense? It's a lot of like, just a lot of words to say all the same stuff, really, is what I mean. So whenever you're asked for the rate of change of a linear situation, we're really just asking for the slope. And when you're asked for the average rate of change in a nonlinear situation, same deal, it's just between two specific points rather than the function overall. Okay, so now we're going to switch gears a little bit and talk about writing equations. So far we've started with equations and talked about different characteristics of the graphs. We're going to now start with some characteristics of the graph and write the equation for the line. We'll start with the two simplest cases, which are really easy to overcomplicate if you haven't seen them before. What can you tell me on this first one? I'm going to write the equation of a line passing through 1, 5 and 1, 9. What can you tell me about those 2 points that's maybe significant? Yeah, they both have the same x value, right? And so if we were to plot them on a graph, I'm not going to mark this up too much, but if one is here, then like one of the points is here and like one of the points is here. So they're going to lie on a vertical line, which means that if 2 points on a line have the same x value, all the points on the line have the same x value, right? So this line is just a vertical line. What's the slope of that line? Yeah, the line does... Can't draw a straight line. There we go. The line does not have a slope, right? So no slope, which is the same as saying the slope is undefined. So the sloping undefined or having no slope is different than having a slope of 0. So this kind of takes us back to the whole dividing by 0 and dividing 0 by something thing. Remember that slope is the change in your y value when you change your x value by 1. So if we move 1 unit to the right on the graph, the change in our y value, the corresponding change in our y value is the slope. But on that line, you can't move 1 unit to the right. right? Like we can't move over, so we can't increase our x value by 1. And if we can't increase our x value by 1, we certainly can't talk about what happens to y when we increase our x value by 1, right? So the premise of finding the slope just doesn't exist. Like we never get to move to the right on this graph, which means it doesn't make sense to ask what happens to the y value when we do. So it's undefined because the idea or the question that we ask when we ask about slope just doesn't make sense at all, which is different from a slope of 0, which is saying when you move to the right, nothing happens to the y value, right? We'll see that one in a second. So this one has no slope, which is kind of a pain as far as writing the equation because we can't use y equals mx plus b if we don't have an m, right? However, it turns out that the fact that we know that every single point on this graph has an x value of 1 is enough to write the equation. So our equation is just going to be x equals 1, which doesn't really look like the equation of a line, but it tells us everything we need to know about the points on this line, right? Every point on this line has an x value of 1, and it doesn't matter what the y value is. So x equals 1 gives us all the information we need to graph the line, which is what an equation is supposed to do, is give you the information that you need to find the points on the line. And so our equation is as simple as that. And then what about this second one? What can you tell me about those points?
They have the same y value, so it's going to be a horizontal.
Yeah, they have the same y value. So we're going to have something like, there's 9. Something like that, right? A horizontal line. So what should that equation be?
Y equals 9.
Yeah, y equals 9. So again, saying that the y value of every point on that line is 9 is enough to tell us everything we need to know about the line. What's the slope of that line?
0.
It's 0. Good. So slope equals 0, which means, again, it's different than undefined because in this case, we can start at a single point on the line and we can move 1 unit to the right. And what happens to y when I do that? It stays the same. So the change in y is 0 when I move to the right 1 unit. And so that is a numerical quantity that exists. So this guy has a slope, it just happens to have a value of 0. The vertical lines don't have a slope. And in fact, vertical lines aren't functions either, right? So we can't ever write a vertical line in function notation. We could write this one as f of x equals 9 because it is a function. So either one of those means the same thing. And that's that constant function we've seen before, right? Where the output is the same regardless of what the input is. So those are sort of like the simple examples where you can just go straight to the equation from the points. I always check that before I do anything else. I'm like, okay, are my x values the same? Are my y values the same? And that way I don't start doing a bunch of calculations just to find out that it was as simple as writing x equals 1 or y equals 9. But if that's not the case, then we're going to use what's called the point slope form of a line. And we're going to use this to write equations of lines, which means that we need 2 things to write the equation of a line. I need to know my slope, and then I need to know at least 1 point on the line. So we're calling that 1 point on the line x1, y1. So in a specific problem, we would have given you numbers for that. And then our slope is called m. When you write the equation of a line, it's got to have an x and a y in it as variables. So those ones will stay x and y. And then we will put numbers in for x1, y1, and m. And that's what's going to give us the equation of a line. So typically they don't just give you the slope, but they always give you information to find the slope. So in our first example here, we have 2 points on the line. And so the first thing we have to do is find the slope of the line. So we'll just use the slope formula to do that. So m, remember that our slope is the change in y over the change in x. And so we'll do the difference in our y values divided by the difference in our x values. And then we have negative 4 over 4, which is negative 1. So now we have our slope. That's m. Put it over here, m. And then we have 2 points, but to write the equation, we only need 1. So you can just pick either one. You're going to get the same equation either way. I usually pick one that doesn't have negatives in it if possible, because then I don't risk making some silly negative mistake or sign mistake. And so this is my x1 and my y1. So we're just going to put those in for x1, y1, and m in our point slope form. So we have y minus our y value equals our slope times x minus, damn it. I'll just start over. We have y minus our y. That was right, wasn't it? It's one of those days. So y minus our y value equals our slope times x minus our x value. There we go. And if you're not told to put it in slope-intercept form, you certainly don't have to. You could leave it exactly like this, but typically we kind of like these to be in function notation, or y equals mx plus b, so that if we want to write it in function notation as f of x equals mx plus b, we can. And in order to do that, we're just going to solve for y. So we'll just get y by itself. So I'll distribute that negative 1, which gives me y minus 3 equals negative x plus 2. And you could certainly write that as negative 1x. And it would mean the same thing if you're more comfortable having that number there. And then I'm going to add 3 to both sides. So we have y equals negative x plus 5 as our equation. Questions? You guys are suspiciously quiet. Is it because it makes perfect sense? Maybe? Yay. Okay, so this is the basic process we're going to use to write all linear equations. The only real difference in the problems is the information they give us to find the slope. So here they gave us 2 points. Next we will do one where they give us a perpendicular line. April, do you remember what Missy Elliott said? So to find the slope of a perpendicular line, you flip it and reverse it, in the great words of Missy Elliott. So you flip the fraction and you reverse the sign. So we say that the slopes of perpendicular lines are opposite reciprocal. So they're opposite signs, and then the fractions are reciprocals of each other. And so if they give us this line, we're going to look at the slope and say we want the opposite reciprocal So this one is positive, which means our slope is going to be negative, and then the reciprocal of 2/3 is 3/2. And so that's going to be the slope of our perpendicular line. Once you get the slope, so m equals, that's the only thing that equation gives you. So we gave you this equation of some other line simply to find the slope of the line we're writing the equation for. That plus 20 means nothing, right? Because if we have, what we've done here basically is given you like some line and then some point down here and asked you to write the equation of this line that's perpendicular to that first one. So where that first line happens to be, like crossing the y-axis, doesn't affect the slope of our line at all, or anything about our line, really. It's just to get the slope is the only thing we get from that line, and then you're going to throw it away. Don't do anything else with that equation. So now that we have our slope, we have our m and we have our x1, y1. So then we can just put that in our point slope form. So we have y minus our y value equals our slope times x minus our x value. And then again, we'll go ahead and put this in slope-intercept form by solving for y. So if we distribute that negative 3/2, we have y plus 3 equals negative 3/2 x plus 3. Because if I multiply 3/2 by 2, the 2's cancel. And then I'll subtract 3 from both sides. And we get y equals negative 3/2 x. What's the y-intercept of that line?
0, 0.
It's 0, 0, right? It goes through the origin because you can think of this as like plus 0 if you want to, right? It just, if I put 0 in for x, I would get 0 for y. What if these lines were parallel? What would that tell me about the slopes? Yeah, they have the same slope because parallel lines never intersect, right? And so they have to have exactly the same steepness or else one of them would like overtake the other one eventually and they would meet. So the only way for them never to intersect is if they run at the same steepness all the time. So we have perpendicular lines are opposite reciprocals. And slopes of parallel lines are the same. And really the only place we're going to use that is to write equations of lines like we did here. So they'll give us an equation of some line and say you want to write the equation of a line that's parallel. And so you're like, oh, I'm just going to use that same slope. Or perpendicular, in which case you'd be like, oh, my slope is opposite reciprocal. And so like all of these questions that ask you to write equations of lines, they give you some piece of information that gives you your slope. And then once you have your slope and your point, you do the same exact thing. You just use that point slope form every time. Good? Here's one for you to try while I hand back your papers. Let's write the equation of a line parallel to and passing through Remember that to get the slope of that line, you got to put it in slope-intercept form, right? Y equals mx plus b. So solve for y. You can't just grab that 3 from in front of the x. You got to get that mx plus b first, and then you can grab the slope.